Hi everyone, this is Meenakshi Ramesh from tapyourwaytohealing.com. Today I have a good friend, a family member, and a guest who is going to talk to us about basal ganglia and autism. So before we start our conversation, I just want to introduce my guest and read his bio. My guest today is Krishnamurti Ganapati Subramanian. He has a Ph.D. in neurobiology from the University of Pittsburgh, Pennsylvania. And he also has a postdoctoral fellow. He's held a postdoctoral fellow position at the Bayer College of Medicine, Houston, Texas, a postdoctoral fellow at Hussman Institute of Autism, Baltimore, a clinical research manager at Virginia Commonwealth University, Richmond, Virginia, head of preclinical research at Alcyon Life. Am I saying it right?
Mhm.
Is it Alcyon?
Yeah, Alcyon license.
Alcyon Life Sciences, Lowell, Massachusetts. Senior Director at Alcyon Therapeutics Inc., Lowell, Massachusetts. And currently, he is holding the position of a Vice President at Celos Therapeutics Inc., New York, New York. So welcome. We call him Sanjeev. Welcome, Sanjeev Krishna, to this topic, to this channel, and thank you so much. I know you're very busy for taking this time to talk about basal ganglia and autism.
Thank you so much.
Um,
It's an
you're
absolute
welcome.
pleasure to come. You don't have to thank me so much. Autism, as you can see, has been one of the focuses of my research, and I've spent a lot of time on it. I'm happy to discuss whatever knowledge I have on that to make it more communicable, all these technical details to a much larger audience. And that has been one of my focuses as well while I was in research at universities, to be able to spread this kind of like outreach knowledge, which I think is very critical and is always a little bit lacking. Thank you.
Very well said, Sanjeev. To begin our conversation, I would like you to talk a little bit about what is basal ganglia, what are its functions, and how basal ganglia is affected in autism.
Perfect. Thank you so much. So, basal ganglia is essentially a collection of structures which are below the cortical level in all of us. So that's why it's kind of like called basal, and ganglia means it's like a collection of neurons. So it's essentially a group of these collection of neurons spread out across like few different structures that are under the cortex. So which is kind of like you can think of it as like the underpinning machinery that helps support the functions of the cortical processing. While most of the research and the therapies, whatnot, are focused on the cortical areas of the brain, which is where like the EEG and all of the different neuromodulation is done. But what helps support these processes are these very complex neurocircuits that underlie the cortical functions. So that's why these basal ganglia are kind of like in a constricted fashion, be able to control everything that goes from motor to cognitive to associative functions of the brain. So it goes from very primordial nature to more advanced cognitive states like thinking, action based thinking, and outcomes, which are the prefrontal functions, which makes us human. And these structures, these basal ganglia structures, are not novel and are also present from like prokaryote, like very um, early on in evolution as well. So even if you go down to look at like sea anemones, whatnot, there are these prototypical structures which are part of these basal ganglia. So they have evolved with us and have evolved in specialized functions for these as well. So a little bit about their association and what they actually do is they've been linked to everything from like eye movements to perception to action to motor generation. So any organism that moves pretty much has these kinds of substructures below their cortical executive functions, as we call, being supported by these. And these collection of different structures go by different names. There's caudate, putamen, globus pallidus, and even within that, there's externa, interna, and all these complicated terms like STN. But essentially, what they do is they can think of it as like a feedback structure. Say the cortex gives a command, the basal ganglia processes it and thinks, okay, if there are 10 different actions, let me pick one of these actions. And it sends that feedback through the thalamus back to the cortex to say, yes, go and execute this one particular action and suppress the others. So that is, in a way, you can think of it as a function of basal ganglia. It is also related to something called action linking, action chaining, meaning that, let's say you start playing the piano. Initially, you will be learning one key by one key how to press one after next. But then after a while, you should just think, oh, I'll play the fou release. And then you would immediately be able to play the fou release. And this process of learning that happens, especially in this case, the motor learning that happens, which is also called motor sequence learning, is what the function of basal ganglia essentially is. It essentially takes all these different learnings from different things that you do throughout life and chunks these, and these are called motor chunks or action chunks, and has these chunks stored as different repertoires of programs within the brain. And say, initially while you're learning, you have to say, I have to press the D key, next the E key, versus once you have it as a learned movement, the cortex essentially says, play fou release, and the basal ganglia will do that function for you. Versus initially you have to learn. Here's where the dopamine comes in as well, which acts as a learning and teaching signal to these subcortical regions. So that's one of the different functions of basal ganglia, where it helps learn and predict what the cortex is wanting to do. Excuse me. Helps make automated movements possible for you. So the example I typically give is, like, say in Parkinson's disease, whatnot, which is where basal ganglia is mostly implied, is you can see that patients with Parkinson's, when you have them, like, say, go move, they won't. But if you point a light to them, there are now walking sticks available which actually point a light. It's called like action guided behavior. If you have them say, like, instructed, go there, they would immediately go. Very similarly, if you put them on a bike per se, you would not be able to differentiate between a person with Parkinson's or a person who doesn't have. They would pretty much be like a normal function because it's an automated repetitive function. It's just that this initiation part is kind of missing in some neurodegenerative and neurodevelopmental conditions. So that's what is typically is seen as like some of the functions of basal ganglia. It's a very diverse set of nucleus, especially when it comes to autism. The example that I can give is, say, in terms of inhibition control per se, if we pick that. Eye movement is one common function, which is now very more easily quantifiable. And if you, say, present a picture, how you look at the picture is essentially you have these short, fast movements in your eyes called saccades. And these saccades can go in a certain defined pattern or in a random pattern. And it's a little bit more not under control in, say, kids with autism versus what would typically be seen when you normally show a picture. These all go back to the kind of executive control function in terms of, let's say, if we take the domain and function of inhibition control. And there are a few different theories that are very prominent and researched on in autism. One is kind of the excitation inhibition imbalance, the other being the long range and short range connections. So if we take the long range and short range connections, as I was explaining in the basal ganglia, it's a very interconnected nucleus connecting everything from the prefrontal cortex to executive functions, to the motor cortex, to motor control, or associative to oculomotor and eye functions. So what happens is these long range connections are typically not as well established. There is some evidence from postmortem data from kids with autism compared to a neurotypical development in terms of these long axonal connections which are not there. And there are also some functional MRIs like the DTI, as it's called, which shows the functional connection between the different areas of the brain. There are some instances where researchers are able to show that the long range connections are not as prominent as you would typically expect. Whereas as a compensation for it in kids with autism or people affected with autism, you would see there is a higher density of short range connections, which is partly the reason why in some parts of the spectrum, you would be able to see a savant-like function in certain particular domains, because they might be very well versed in, say, for example, numbers and be able to calculate and remember numbers. and which also goes with the synesthesia, where they see numbers as part of the colors or textures, that they can remember long sequences because they're adjacent to each other, and how they perceive, say, a number two would be very different than, say, how we would perceive a number two. And I know I mentioned a lot, and I know this answers some of the questions that we started out by talking, but happy to expand on any and all of these in terms of like what questions you have or what would be more beneficial to help explain in further detail.
Sure. Thank you so much, Sanjeev. This is like it's very eye-opening, and I'm as I was just listening to you, the question that popped in my mind was, um, any function that any of us do, whether it is speech or speech language communication or social skills or just performing any task. I think the basal ganglia is the key structure that's involved, I feel. So this brings me to the topic that, every action that we perform, it involves a series of movements. And what I notice and I hear from other parents is, individuals on the spectrum, for them, for some of them, it's very difficult for them. They're challenged to make meaningful movement. And the other challenge that we commonly notice is, one is not able to make a meaningful movement. The other challenge is not able to complete the movement. So basically, beginning a task and having the challenge of not being able to complete the task. In other words, not being able to complete the movement. So if you can talk a little bit about that, I think it will be very helpful for the
Great,
audience.
excellent. Yeah, the part about beginning of movement, definitely there's a lot of scientific evidence around that. So it's typically called goal-directed movements when we mention like what happens or what basal ganglia is supposed to do. And the example I gave before, as well as what it's an easy to remember example, like say, if you ask someone to walk, they would not be able to walk, say, if they're affected by Parkinson's, versus if we have them to say, like, take a left leg first, keep it down, keep the right leg next, whatnot, they would be able to follow. And that particular function is guided by basal ganglia. So that's where the goal directed movements per se have a very prominent role in basal ganglia. And these long range connections, if indeed they are not as prominent, you might not be able to get that signal to these underlying different structures to say, yes, go ahead, make the left movement first and the right movement first. This is related and tied to the learning function of basal ganglia, as I mentioned. Here's where the example of learning a keyboard is very simple to understand as well. Where initially, when you start playing the keyboard, you'd say like press D, then E, then D, then whatnot. You learn these one by one sequences. And then eventually, all your prefrontal cortex or your conscious memory, if you think of it like what you consciously perceive versus what you execute, initially you would be like, I need to press D, then wait, then press E. Versus later, as you become like a virtuoso, all your cortical brain needs to tell you is play for release, and then you go play it seamlessly. So that
Right.
connection between like how you learn step by step to continuous is definitely a function of basal ganglia, and is becoming more and more well accepted that that indeed is what these learning signals of dopamine in basal ganglia does, that it helps program these. And another function, as I mentioned, is chunking. Here's, this chunking is where I would relate it to in terms of not being able to fully complete the movement. Let's say
Mm,
there is full release, it's like a 2 minute piece or a 3 minute piece.
mm,
You have these 2 3 minute sequences being broken down into like a 1 minute segment or a 2 minute segment, or easy to remember motor sequences that your body needs to perform.
mm,
So what happens is these different sequences are stored differently. You can conceive it that way. And your brain just says like play few release, and your basal ganglia essentially goes into action, says like, start inhibiting these circuits, start activating these circuits, and then follow it in this pattern. And say, for instance, these long range connections and short range connections are not as well defined. You might be able to initiate, say, even from external prompts, but you might not be able to sustain it to continue the entire piece, because after X sequence, the Y sequence needs to go, but that again needs a separate prompt. And then once you have that separate prompt, the Y sequences go through. And then you'd probably have be waiting and halting until you get a signal saying, okay, go do the Z prompt. And then you would do the Z prompt without any issue at
Right.
all. And here
Right.
again, the example I can think of is like the biking, where because it's a continuous series of movements, say someone who's impaired with basal ganglia function, like a Parkinson's patient, initially you tell them to write their own, but if you give them the prompt to say go and you push them, they would start biking like you can't differentiate between a normal person, because then it becomes a continuous sequence of movements. It's self-propagating. So it's getting to that and bridging that is where some of the interventions and the different therapies can help as well. One of the things that I worked on is also something called multisensory integration, where you have to integrate a few different sensory organs, like say your eyes, your kind of perception with your motor. I also did something called audiovisual integration, where we can see differences between like how you normally integrate audiovisual to someone who has these kinds of inhibition control issues in some cases, or in the case of like sequences issues, or even like an initiation issue. The weightage that you give for the different inputs that come in could be very different because they perceive the inputs differently as it comes in as well. So it needs to be tailored for each specific individual, mainly for that reason. Hence, it's also a very diverse disease, excuse me, which comes with its own set of consequences in terms of how
Right.
treatment is done and therapy is done. And with the most recent advances in like where the science is going currently, which is where like the genetic or the monogenic diseases are getting far more prominence in terms of, let's say you have a specific gene tied to some sort of specific marker, let it not even be like a clinical benefit. As long as you can correct the gene through a gene therapy mechanism and show a benefit to the marker, we believe there may be some clinical benefit. And even yesterday, I should say, one of the drugs for Lou Gehrig's disease or ALS got approved on that basis, on an accelerated approval, which would have been like unbelievable, like say even 5 years ago or 2 years ago. So the regulatory agencies and other organizations are also becoming more aware of the need to bring these kinds of more avant-garde treatments, so to say. And it's also harder in the case of diseases like autism, partly because there's no established connections. And being able to establish those connections, being able to bring these kinds of quantifiable biomarkers or clinical benefits, like say how to benefit communication even through like communication devices, whatnot, and being able to say like, say you go through this therapy, you have better communication even through an assisted device. That would be beneficial for these kind of inhibition controls we are talking about, or how to continue the sequences, things of that nature. Those are all definitely things in the arena of what can be done to help. And obviously, as always, early intervention is better, early diagnoses are better, and there's definitely a lot of progress made in that front. And that definitely helps with kind of both understanding and the biology of these diseases. And I know more recently there's been this classical autism definition versus the more extreme spectrums or more milder spectrum, so to say. So that is also a good development in the field. So you can better classify and understand a subset so that way you can go after specific biological mechanisms. There's some of the few challenges in why it's been harder to find treatments or make headway significantly in this particular condition. So.
Right, right. So when you were talking about the prompts, the signals, it comes back to how when we start early interventions with all these children, it everything begins with prompting. Everything, every little task, activity, sit down, get up, can you let's go here, and it's shadowing, really, go home, doing hand over hand things. And as they grow older, we do see progress. We do see progress and improvements in every individual in their own pace. They're all learning and improving and progressing in their own pace. And we also see prompt fading. That's the ultimate goal. All these interventions, early interventions, the ultimate goal is to eventually fade out the prompt, so that the individual is able to carry out and make those meaningful movements or complete those movements and complete those tasks with with no prompts or minimal prompts, which brings me to the question that about neuroplasticity and neural wiring, neuroplasticity and the how do I say it? I shouldn't say wiring. What is the term, Sanjeev? That
Like how they
connection,
develop
neural
and grow.
connectivity. Yeah, yes,
Mhm.
yes. Could you
Yeah,
talk
I
a
can
little bit
definitely
of?
give you an example for it, even as it relates to autism. And this
Yeah.
definitely I can say like it's technically called like automaticity in basal ganglia, where I was saying like initially you have to press the D key, E key, and whatnot to go, whereas it becomes very automatic as you
Automatic.
learn the whole sequence. Your
Mm,
cortex just needs to say play through release, and then your
mm,
hands automatically go forward. And that's what I mean by like chunking or putting a few
mm,
sequences together, and then you don't even
mm,
think about it. It's not in your conscious brain to do. A simple
mm,
example of it is how we learn to walk. And if
mm,
you and it's now mostly depends on again like the different spectrum and the learning rates for individuals, that kids with autism typically take slightly longer for their walking and developing those
mm,
skill sets for motor behaviors as well, which is definitely one of the
yeah.
earlier ones to show
Mm,
externally, is partly
mm,
because this kind of chunking and this behavior takes time. And exactly as you said, the prompts will eventually go away, which is where like the therapy and the multisensory integration and even doing handover and helping the kids and individuals grow is going to help, because it repeats the same process again and again. That's
mm,
what basal ganglia does. It essentially takes these
mm,
repeated process, like first you
mm,
have to lift your right leg, then you have to
mm,
contract your glutes, then you
mm,
have to relax your hamstrings, whatnot, the internal individual muscle
mm,
by muscle sequences. We don't need to do it. While we were learning as
mm,
a little kid, baby, we had actually done it,
mm,
and that becomes an automatic sequence. But it takes a much longer time because of either these long range connection, short range connection theory, or an excitatory inhibitory imbalance, because basal ganglia is essentially like an inhibitory circuit that goes back to the cortex to feedback. It just takes longer for some of these kids to learn these, and that is
mm,
indeed evident by their slower progression or a different learning rate compared to what you would normally expect to see from these. Hence, like
mm,
interventions that help these faster would obviously help the kids be less prompted to walk,
mm,
to
mm,
communicate either using assisted devices or on their own, or be able to play
mm,
without or play
right.
sequences of keyboard whatnot without any external prompts. So that definitely the repetition is key,
Mm,
and part of this
mm,
automaticity is what basal ganglia does, and that is something that
mm,
I'm more or less convinced, and I'm sure the field is also more or less inclined to say that's part of the function of basal ganglia as well. So
mm, mm. This is very exciting, Sanjeev. Even as I'm talking to you, I hope parents who have very young children who are watching this, uh, I want to say that there is hope, that there is hope, because I think as humans, we are all, the brains, they say that the neurons keep connecting they never stop, right? As long as we are
that's exactly
giving the
right. Yeah, and to
stimulation. Yeah. Yeah.
yeah.
What I was getting to was the neuronal connection, they say the neurons fire
The
together.
plasticity, yeah, I didn't
Yeah.
address
Yeah.
that point
Yeah.
explicitly, but I can tell you that yes, it
Mm,
takes longer for some kids than others. And if you
right.
think about it, even as whatever we call normal or neurotypical, we
Mm,
have our own
mm,
different rates as well. It's just that they're in a
right.
different dimension than us. So
Right.
that window is just different for different people. Some people are
Right.
quick learners, some people are not. It's the
Mm,
same for kids in the spectrum as well, I would say. And in that
mm,
regard, there are now new treatments, therapies available. I currently work in a few different mechanisms where this plasticity
mm,
does not go away. It does stay
mm,
in the brain. That's the nice thing about the brain, is that it's a very plastic organ. You can
mm,
always remake these connections, these synapses,
mm,
whatnot.
mm,
But
mm,
the limitations of that is once you're born with a set of neurons and connections, those typically
mm,
stay that way, but the
mm,
optimization between them would be very different. So say the way
mm,
you, let's say there are not long range connections as much as say if that
mm,
theory is true, you can make
mm,
multiple small short range connections, and that can instead substitute for your long range connection. It's just a
mm.
different way of how you're wired, so to say.
Right,
And you
right,
just need
right.
to learn how to make those small short range connections, and that's what these
Mm,
treatments and therapies do. And I definitely do believe that's the direction the field
mm,
is heading as well. And
mm,
there's a lot of treatments and therapies that are in that space. And I can recall like even like a few companies that had reached out, like where you had these virtual headsets that You can kind of like, just like you're saying, hand over hand, you let them be in their own virtual world, but you act as their guide, helping them make these movements for them. So they kind of see what needs to happen, but they think they're doing it, but it's their prompt being held by their caregiver. So I've worked with a few different
Wow.
startups that work in that domain as well, like especially in autism. I also teach them with how to interact with cops, because safety becomes important in terms of how you interact, and get them to learn some basic what needs to be done in certain situations. So there are a lot of different companies and eventually what do you call, behavioral programs being now in the domain as well. And it's now even approved by CMS, whatnot. So you can actually get codes for it and be able to get insurance to cover some of these as well. So those are all definitely very much a progress in the right direction for not just one, but multiple different therapies that can help treat kids. So.
Awesome, awesome. So what else did we want to talk about? Could you talk a little bit about basal ganglia and sensory processing, and in general processing, you know,
Excellent. Yeah,
how
yeah.
it
So basal
affects
ganglia is
processing?
a
Yeah.
very nodal part of sensory motor integration, I would call. And sensory processing, as I said, is a very complex topic in terms of how they perceive is very different, as I mentioned. We do know that based on some of the work even that I did in multisensory integration, like if you have an audio visual cue coming in at the same time or mismatched, how we perceive it and weigh it is very different from, say, kids on the spectrum too. And that could be because of multiple different reasons. And I'm a big fan of something called corollary discharge, which is kind of what happens is, let's say you make a movement, your brain essentially sends a command saying, move your hand, but then there is the command going, and there's also a backward sensory perception that goes back to your head. And that backward sensory perception is what is called corollary discharge. Although your brain says go and you're going, you don't perceive it until your sensory feedback goes back to your brain to say, yes, it is gone. And this discharge happens all the time in all the processes in the brain. And this is called corollary discharge. And these corollary discharge mechanisms are sometimes a little different and modified in kids in the spectrum. So it is either lag, meaning that they have a different perception of the same, or it takes a longer time for them to understand, which again goes back to the long range connection versus the short range connections. So that I think is kind of like a fundamental change in how they perceive, which is why, like, as a kid growing up, if they perceive it in a certain way and they were taught in a certain way, they are fixated on that and they would like to go back to it, because that's how they can make sense of the world, not like how we do. Partly because the way they perceive is just very different. Their processing has just been brought up that way. One example and kind of anecdote I can think of is like I know audio and audio perception is one of the primary kind of concerns for parents, because that provides sensory stimulation, which leads to unintended or not exactly prompted movements. So sometimes kids wear these kinds of headphones with a certain frequency to help bring that down. So that's a way of their brain being tuned to being able to only work and perceive at a certain frequency of hearing. And as they grow up, they still continue wearing those headsets. And I can think of a prominent kid with autism who grew up and is now an adult. He still wears those headphones to help him prevent from those. And which means anything that happens within that frequency, he's now able to build those kinds of sensory processing or control the processing issues that's typically seen, to be able to inhibit the others. In this case, assisted by this headphone, which only filters out a certain frequency that comes in. So then he's able to have better control as long as it's within that frequency. That helps at least tune the brain to a certain parameters of how it can function within, say, the person's control. Just as an example in terms of how the sensory processing is impacted. And that definitely growing up will play an impact. Like, say, growing up, if they were wearing a particular set of like, so within a certain frequency filtered out, they would only be able to match that. Yes, you can expand it over time, but it just takes a different, and as I mentioned, like longer, and those plastic connections can happen and eventually even get out of it. But you need to learn from some basis to say, like, you're working well within this environment, within this particular set. Then you can slowly expand it out to a much more calmer environment, before you say you put them in a rock show and then say, like, go do it, rather than providing too much sensory stimulation. There's some examples of how sensory processing can also be impacted. And it's because of the connections, how they learn and how they process still needs to be integrated and slowly expanded out to different scenarios.
Right, right. Um, which makes me think that as you were talking, as I was listening to you, I could see I've seen many children and my son, like, just to cut out from the external, the chaos and the noise that they are hearing, a lot of, echolalia, and a lot of, verbal, repetitive, saying the same thing over and over. So all those are typically coping mechanisms. That's how they cope with, like when you were giving the headset example, I was thinking, like, there are some children who just like do this. And it's very, sometimes, as parents, it can be very difficult when we watch, or even in the school system, because we feel that is interfering with their focus. But that is just one way they cope up, just to, coping mechanism to filter out the external, the overstimulation that they are experiencing, that their nervous system, they're just protecting themselves so that they're not thrown off by the sensory overload. And finally, I just want to talk to you about any medical interventions. I know that's the last route that parents want to go to, but, if you have anything to share, please do share. Yeah.
Sure, absolutely. I've worked on a few different, including in some collaborations with, like, the prominent big pharma, Roche, on balovaptan, which is a GABAergic drug. One thing that I can share from my own research is that I've looked at multiple kind of different changes in the receptors in the brains in kids with autism versus what's typically seen. And what happens in basal ganglia is the exact opposite of what you see in the cortex, meaning that, like, say, GABA A receptors are significantly high in one portion of the brain. It's the exact opposite, significantly lower in the portion that connects to the basal ganglia, which means a chemical intervention of, say, like, increasing the GABA is going to have the opposite effect on other circuits, which are kind of unintended, which is partly why, like, the balovaptan drug and the other GABAergic interventions did not work. As I was mentioning earlier in this uh, piece as well, is that being able to find a genetic connection is one way forward. And I know there are some examples. For instance, say Rett syndrome just got a drug approved last week. There are certain conditions where at least some small parts of the, say, repetitive behaviors or being able to calm, it's more symptomatic treatment, unfortunately, not necessarily addressing the core traits or issues. And that's partly because of the diversity in autism per se. Being able to have some sort of a quantifiable metric, like oculomotor is something that I know you've mentioned, and, like, the eye movements is something very prominent because there are very quantifiable metrics and measurements you can do, and definitely calming those systems can help. And I know parents would obviously try anything to make sure that it works, and that's why, like, I do not want to go into any specific particular therapy or something to say this is much better than others, whatnot.
Right.
I do have seen some betterment with, like, just overall just calming them, because that, as you mentioned, like, even them coping up with their own kind of like repetitive behaviors, whatnot, just helps them understand the world in the way that they see it. And I would say that's not any different than, like, say, a regular kid as well, because I've seen, like, just going back and forth and rocking is what normal kids do too. Except it's just like, just because they're not called within the normal or whatnot, it's just being seen and perceived differently. So there are interventions coming up. I would definitely say, like, even if things like Rett and whatnot, if you can have some interventions, it would definitely help with, like, more of the more broader autism spectrum disorders.
Okay, so any final thoughts that you want to share with parents, with the audience watching this, having worked in the field of autism?
I would
Any
definitely
tips, any
say
advice,
the three
anything?
key things would be, like, always watch out for, like, the early development milestones, whatnot. So early diagnoses is key. And being able to provide interventions early on in terms of treatments and therapies. And finally, I would say, like, do not lose hope, as you were saying earlier, that there is obviously lots of interventions, lots of different approaches and therapies coming on to help, including medical, pharma based, or otherwise as well. And I do see a lot of activity now in terms of assisted devices for communication, especially for the classic autism cases where they're non-communicative. So definitely work towards those so that way you can at least have some sort of connection with the kids and people who are suffering from autism.
Awesome, awesome. Thank you so much, Sanjeev. Thank you for sharing your insights, knowledge, and wisdom. I appreciate you again, once again, taking the time to share this for my channel and with the audience. Thank you.
Thank you
Let's
so
stop
much. And please
recording.
share the paper with your viewers as well. Happy to share
Yes,
that.
yes,
They can go
yes.
into more detail as they need.
Yeah. So if you're interested in, reading the research paper in depth, so please contact me and I'm happy to email the research paper to you. Please contact me. All right. Bye.
Thank
Let's
you.
stop recording. Thank you.